Hi everyone, welcome back to our channel. I hope you and your family members are doing good because that is the most important thing, and for us we are here to talk. So we were following binary tree, pattern was BST, and let's do the next question, which is search in a BST. So here is a problem statement. As we have already saw in the previous video what is BST and how to construct BST with a sorted binary tree. Now let's suppose our binary tree has been created and now our task is to search any value in the binary search tree. Okay, very simple. Let's read the constraint. Constraint is the minimum number of nodes can be 1 also, and it can go till 5000. Okay, and node value can go up to 10 power 7. Okay, why we read this? Because if we have to manipulate or do something, like summation of the node values or multiplication, then 10 power 7 will get added multiple times or get multiplied. So it might go beyond 10 power 9, which an integer cannot hold. So hence we have to convert this in long format. But here in this question, we are just looking for, the find operation where we are not allowed to manipulate any value. So hence 10 power 7 is totally safe. Okay, so let's move on to the problem. Obviously, the question would have given the root and the value which we have to search for. So here, let's say the value is 3. Okay, so if we have been given 4 as a root, so don't you think like if we have to search value 2, let's say value 2. Okay, so we are at very first node 4. So do you think we should go towards left side, right side, or we should check the root first what if value matches? Can I say that? But before checking the value, don't you think we should check what if root exists or not? Correct? Okay. So whatever you are able to understand, just write it down. What? First, to match the value, the root should exist. What? If root is equal to null, we have to return. Can I say that? Okay. We have to return what? Simply, we are not waiting for anything to return. So if root is null, return root, which is null only. Okay. So what I said, if root does not exist, it does not make sense to check the value or to go towards left side and right side. Now, if the root exists, okay, now there can be two conditions. If value matches, return the root itself because the value has been matched, right? So no need to go towards left side and right side. And if the value does not match, then only go towards left and right side. Can I say that? Because our task is to search for value. If the value matches at the very first root, then no need to go towards the left and right side. Just return that root from then and there. Can I say that? So can I say here, or root dot value, if this value matches with the original value, then return root. Why? See, if root null, then we'll return root, which is null only. Or condition, this will get checked only when this will become false. And if this is false, means root exists. And if root exists, we are free to check the value. So we'll check if the root dot value, suppose it was 2 only. So we'll check, yes, the value matches, yes. So return that. So return this root, which was expected also, okay. But here it does not match. Okay. So it will say, no, it does not match. So now what is our task? Go towards left side or right side? Do you think we should go towards both sides, or we know because it is a binary search tree and because it will be in sorted format, so we know we should move toward either left or right side because the value, which is 2, is shorter than the root value. So for sure 2 will be existing towards the left subtree instead of right. Can I say that? Yes. So what I'll do, instead of checking on whole tree, we'll check only at that part where it can possibly be present. Okay. So if my root dot value is greater than what? Value, means value is shorter, then I'll go towards the where? Can I say left side? Means basically I'll have a DFS function which is root and I'll be traversing with the value. So basically I'll call the same DFS function again with the root dot left and value as it is. Very simple. Now what will happen? I'll go towards left side. Now here again it will check, is my root null? Root value matches with value? Yes. So what I should do? Return root. Okay, so return root. So as we have called here, do you think we should save this root or we can simply return from there only? Hey, return. So 4 will also say, okay, return. Understood? Okay. So hence, when you are calling this with a return statement, call it. Very simple. Or else, suppose you have to find 3. Okay. So when you have to find 3, what will happen? It will say, is the root value, which is 2, is greater than value? No. No means this value, which is 3 you are looking for, will not be present towards the left side of 2, but it will be present towards right side. So basically it will go in an else condition. You can simply say without else also, return, call the same DFS call. Now go towards the root dot right, means right side, and with the same value, and that's it. Yes, that's it, you're done. So basically what we did, let's visualize this through stack call. In the stack call, first function 4 with the, we were looking for 2 value, right? So this will get saved. We'll try to match. No, it has not been matched. So as it is 2 is smaller, so it will be present towards left side. So we'll go towards its left side. So function 2 and 2 will get saved. Now here we'll check what is this. Is the value 2 matching with this? Yes, it's matching. Okay, so return root, which is 2. Okay, now 4 will also say, okay, return whatever you got, which is 2. 2 root means 2, 1, 3, entire subtree will get returned. That's it. Yes. Now, if suppose we were supposed to find 3 instead of 2. Suppose we were supposed to find 3. Now what will happen? After 2, we'll check the 3 is greater, so it will go, we have to go towards right side. So we'll again call function 3, let's say 3, 3 all. Okay, function 3 and 3. Now we'll say, yes, we have found it. We have found it. So we'll return 3 from here. Now this will return 3 to this, and this final call will get returned 3. 3 means only subtree 3. Okay. So what is the time complexity and what is the space complexity? Space, so we all know because of the recursive call log n space, because it always stores height, many number of calls. But time complexity, will it be O of n? O of n means, actually, do you think we visited every node to check for 3 or 2, whatever? Or we visited towards first left half, means we ignored right half totally. Okay. Then after this, we ignored left half totally and we traversed towards the right half. Means, can I say, like here though the number of nodes are just 1 towards right side and 3 towards left side. But suppose in the, where complete binary tree, it's a complete binary tree and all the number of nodes are filled. Let's say here also, okay. Let's say some value 5, 6, like this, anything. Okay, so can I say if we have to find 2, so in the first step, so we have ignored whole half of the nodes. Now again in this, we have ignored again half of the nodes. So what is this? This is nothing but first 1 by 2, then 1 by 4, then 1 by 8 and so on, which is nothing but logarithmic of n base 2. Yes. So we have not visited every number of node to find or to look for a node in BST. We have only moved to either left side or right side until it matches. So in the worst case, we'll end up moving on every levels for 1 node. Obviously 1 node, because at first we started with 4 only. In the second level, we have either moved to 2 or 7, right? So we chose 2. Now in the third level, we can either move to 1 or 3, but we chose 3 to match it. So in every level, we have got only 1 node to traverse, right? And that is nothing but height. And height is nothing but number of level, means logarithmic of n. So hence, the time complexity in BST to search will be logarithmic of n, and space complexity will be logarithmic of n because of the recursive call stack. Now the question is, can you reduce the space complexity to O of 1? And that is only possible when you're not using the recursive call. Can I say that? So when it is possible when you do not do recursive calls, but you can traverse on left side or right through iterative approach. Yes, iterative approach means you will start with the root, right? Now you will move, like first you will check, does this root value matches? No. Okay. So move towards left side or right side. So move your left means if your root value is greater than value, listen it very carefully how I am doing it. If my root value, which is 4, is greater, is it greater? Suppose we have to look for 7, then no. Is it greater? Means 4 is greater than 3? Yes. Means 3 will be present towards left side. So simply move your left to root dot left. Else, suppose you are looking for 7, then this condition will fail. So simply move your left to root dot right. Now suppose you are looking for 8, so what will happen? Here so 8 is not present, so from 4 you will go to 7. Now you have to go for, you are looking for 8, right? So you will go towards right side and now you will get your root null. So can I say you should stop? So what will be the stopping condition for this? Until your root becomes null, keep running it. Yes. So what you will say? You will keep running while your root is not null, keep moving. But this is though for moving left side or right side. But the earliest I'll be present at some node. So first I have to check what if the value matches, then to return then that root then and there. So very simple. First, if root is equal to, like if root dot value is equal to value, return root, or else move left and right. So in this case, what happened? You have actually traversed in the tree only, but using the iterative approach. And because of the iterative approach, you have not saved your nodes anywhere or number of calls anywhere. So hence the space complexity will become O of 1. But the time complexity will still remain logarithmic of n. Why? Because here also you are deciding whether to go and you are only choosing one node, ignoring the rest half. Correct? So hence this was the simplest code. I hope you can do. Now let's write the code in the editor. So let's write the recursive code first. So what we'll do first, so our task was to check base case, right? Okay, what if my root is equal to null, or my root dot value is equal to value. So in both the cases, I have to return root, because if it is null, root will be null and it will get returned. Now our task is to check, like obviously if this if case does not pass, it means root was there and the value does not match. So our task is to go towards left and or right. So we have to check if my root dot value is greater than the value which we are looking for, then we have to go towards the left subtree. Means I'll call the same search by BST tree, but now this time we will go with root dot left as root and value will be as it is. Or else we will simply call this with the root dot right. We'll go towards right with the same value. That's it. Now let's run the code. I hope you can do this. It was very easy, I believe. And that's it with the Java code. Here is your C++ code and here is your Python code if you're from Python. But now the condition is how to do iteratively, because that will save our space complexity, right? So we have to simply write while our root is not is equal to null, correct? Is not is equal to null. The very first thing which we have to check is what if value is matching with the value. Then and there return the root as it is, correct? Or else our task is to go towards left or right. So if our root value is greater than value, then we have to go towards left side. So root will be root dot left. Okay. Yes. Else. Why we have to put in the else? Because we are not returning. Okay. So root is equal to root dot, root is equal to root dot right. That's it. Yes. And if we'll not find anything, what we should return null, right? Now let's run the code. That's it. Let's submit this. Time wise, both will be same. Only the space wise, it will be more, as it is a constant space. So it will be space optimized code basically. So I hope you can do this on your own. That's it. Let's mark the next question. That's it for this video. And the next video we'll do the next question, which is insert into BST. So stay tuned for the next video as well. Till then, keep learning, take care of yourself. I'll attach the sheet link and my social media links in the description. If you really like the video, please do hit the like button and subscribe the channel if not yet subscribed. That's it. Let's meet in another video. Till then, keep learning, take care of yourself and your family.